physics video presentation. Where to start? Anyway, we'll start with a little bit of Bill Gates on the ether, and then go to relativity and more importantly, the Eddington experiment, where the Van Briesen guy is going to do it again, another video, under a different subject category, where he's going to explain it again, and I claim likely inaccurately. And Bill Gates is very good at pointing out a lot of the flaws in the conventional model. They can't even get the historical record right about anything, who invented it, who did this, who did that. It's all just a story, basically, an inaccurate story. The real heroes are left in, the ash heap of forgetfulness, and it's all this hype and trying to make gods and deities out of humans, the heroes, and it's it's just bad. And even science is guilty of it, which is something they shouldn't be guilty of. They should be able to get the truth and the facts down right, and without exaggerations and hyperbole and statements like "just trust me." I watched the rest of the Al-Kahili video on nothing and something, and it's just full of "trust me" statements. Oh, trust me, the nothing creates particles. We're certain. Kind of crap like that. You're not going to provide me any evidence. You're just going to tell me to trust you. Oh, okay. Yeah, forget it. I'm not going to do that. So anyway, Bill is useful in terms of setting the record straight on some of the crap history. Not too good at replacing the mush with something better. So I'll sort of get to that, because he can't even really describe the key distinctions in ether theory, where the concept comes from and why the concept has nothing to do with particles, even though the ether is claimed to be made out of particles. It's not particle physics. Ether theory is not particle physics in any rational way, because it's completely dependent on some sort of magical functions that there's absolutely no evidence exist. And that's why regular physics can't say the word ether, because it implies something they know isn't true. And I suppose I should explain that. So, there's always something with this camera. It doesn't allow me to do a damn thing. It's fucking always editing my work. Anyway, so the theory is that there's a something, whatever, ether, whatever the hell that would be. Now, I just analogize it as some sort of, jello that vibrates, right? But we know that when jello vibrates, we know it's not, we know there's little atoms inside the jello. The electrons are putting pressure on each other on the outside of the atoms. The atoms are, moving away from each other. They're transmitting each other's movement. One can't move without moving the other piece of jello, without moving the other piece of jello. The concept would be, if this one moves to here, this one gets uncomfortable and he moves this way, or he moves this way, or he moves this way. And there's rules about whether something moves in a straight line. The faster this little fella moves, the more likely this little fella moves this way. And the slower this thing moves, the more likely it is to move one of these other directions. And so that could be a simple rule of the tension between bits. Now, that's a tension created by clearly an external pressure, the air pressure, whatever you want to think of it as. The molecules, the atoms are in a container. Now, the opposing thing would be that, yes, the atoms are capable of being repelled by each other because they're covered with electrons, but they're also capable of adhering to each other because of the protons and the electrons. And obviously the atoms can have a tendency to connect to each other by sharing an electron. And then you have something a little more cohesive, where all the little bits are sort of connected to each other. And you have strong bonds that have more than one electron in them, or you can have weak bonds. And weak bonded substances Now, obviously, it becomes clear that those bonds can move and turn. You know, the atom can be in this position, or the other atom can be in this position, or it could be in this position in terms of where the bonds are. And clearly, you could move a force. You could push one of the atoms and therefore cause this atom to move this way, or you could cause it to move that way. Or, again, you could cause the energy to move straight. And again, the principle is, the common simple rule is, the faster you push, the more likely it is your push will go straight. So that's like the wave. So if you're pushing a wave, you can get a wave to move as long as you push fast enough. And I would argue that that's why it works in sound, that you have to create a movement of an atom that's faster than sound. That is the speed of transmission. So you have to break the sound barrier in terms of the speed of the motion. And then you'll create a wave that perpetuates reliably straight without the energy being lost going in all kinds of different directions. And so everything we hear is fundamentally made out of little tiny sonic booms, which is movement of atoms faster than the speed of sound. Therefore, they perpetuate that energy. And you know, like I said, I think the examples can be understood. Everything can be understood as anything that produces sound can be understood as molecular movement that's faster than the speed of sound as the real cause. So that analogy is used for an ether, as if the ether is made of a bunch of particles that are either compressed into each other, you know, held together by tension between them, or held together by attraction, okay, connection between them in terms of sharing electrons. So there's either one of those two mechanisms. And so somehow they're saying there's an ether, that is a substance in the universe made of some sort of particles that are completely undefined, and that the particles are connected to each other. Now, obviously, I would argue that's nonsense, that the real force, okay, is, yes, it's particles, but it's little bits that are not connected to each other, and in no way are connected to each other. They have no force is ever connected to another piece of force, and that's why the forces don't interact with each other and or themselves or anything else unless they hit matter. So they have to interact with a piece of matter for them to change their direction, for them to reflect, or for them to deflect, or do anything. They have to actually hit an electron or a proton. And there's no ether, there's just forces made of particles, little bits of quanta of momentum. And the same rules apply in the sense you can move the momentum straight if you have enough momentum. And if you don't, and you have a system of pressure, that is, there's another electron here, well, obviously that's going to mean that you might deflect, change the direction of your motion. And that's what the ether contains. And so this idea that there's something called a photon that's some sort of stupid wave, you know, floating around, you know, just some sort of whatever this is, right? This exchange happening in some ether, there's just no explanation. We know why atoms react. Like I said, we know that two electrons have a strong repulsion and two photons have a strong repulsion, and that the attraction is between the electrons and the protons, and that can be understood as an absence of pressure between them. And the pressure can be understood as two ping pong paddles with a ball between them, and the closer the paddles, the more interactions, the more pressure. So you can understand pressure on the charge level, the material level. You can't understand it as anything on this subnuclear particle level of forces. And certainly in ether, the idea of a wave that's contained, that you contain, that you don't allow it to ever spread outside of this consistency. I mean, photons have consistent polarization. They have consistent features. And they have every appearance of just being cannonball, 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 all flying in a nice straight line. They don't have any appearance, and I would say cannonball, 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 cannonball to account for polarization. This is the polarization. Cannonballs are a little bit out of alignment. Simple description. And this is their frequency, is their wavelength, is the distance just between them in space. They were launched at a different time, and that's it. That's a photon. That's particle physics. And so there's this huge, I call it, that's some kind of disconnect, where the assumption is that some sort of ether has functions of charge, where the objects are repelling each other or attracting each other to be able to be connected. So the understanding is that there's two ways of looking at it. Particles that are independent, that kind of particle physics, they have a momentum, they go from point A to point B in a straight line unless they interact with matter, or some sort of ether where these little particles are somehow all connected to each other. It's this whole bunch of these little particles connected to each other, and then somehow they're transmitting the energy. And as I pointed out before, if you try to make a matrix of ether, you lose the consistency of straight lines. This distance becomes longer than this distance, and it just breaks down as a rational description, because you lose the rock solid connection between distance and time. Just change the direction, and all of a sudden you've changed everything fundamentally. So it's really annoying because people like Ken Wheeler will talk about a theory of bumping particles, and then this guy will do this theory of bumping particles. There's nothing wrong with a bumping particle theory. There's something wrong with giving the bumping particles attributes they don't have, material attributes. Giving forces attributes of charge is not, that's not bumping particles anymore. That's bumping magical forces. So, so we'll play a little of this.
It's an ether. It's a bunch of particles. And anyone who disagrees with my definition better have a good definition for the ether. My definition, bunch of particles. Keep that.
Yeah, so I wish it was. I wish their definition was a bunch of force bits, a bunch of little tiny bits of momentum, okay, that can be in arrangements. There's a photon because it's in a consistent arrangement. And when they're not consistently arranged, when they're coming at all kinds of different rates, then it's gravity. And it can be magnetism if there's two kinds of the force. If these are electron force bits, then they'll move an electron. If they're proton force bits, they'll move a proton. And I've already been through it, but if they're, if it's a like bit, it bounces off and gives momentum. If it's an unlike bit, then it deflects, and the momentum's in the wrong. It's in another dimension, and that explains magnets and magnetism and electricity. But this idea that the force bits bump into each other is nonsense. The force bits bump into electrons and protons. So particles work. You just have to describe the particles in some other sense than being water molecules that are stuck to each other. The force in the universe is not a cohesive, connected force. The force is little independent bits of energy, and quite different.
That in mind. Okay, so what is the ether? Well, here it is, bunch of particles, okay? I've shown that in the past. What is waving there? Well, that's the so-called wave, transverse wave, longitudinal wave, whatever wave you want to think about there. What is it, the waving of the ether? What is the ether? A bunch of particles. So what's wave?
So again, the particles for ether to work would have to be connected to each other. They'd have to either be adhering, sticking to each other, or they'd have to be confined by pressure, and therefore, and still repel each other. So there has to be tension between the individual bits of momentum. I would argue that a good particle model concedes to, what all the experiments indicate, that the ether, the fundamental force, has no adhesion, no connection to each other. One piece of momentum force has no idea what all the other force bits are doing and will not affect the other force bits. It has to actually hit a piece of matter to do anything different in the universe besides move in a straight line. And straight lines explain all the curved lines you ever see. If you see a curved line somewhere, there's a straight line that explains it. Straight lines of force.
Being a bunch of particles. Okay, that's what the ether is, and that's what quantum, what general relativity, they're all the same. They all say it's ether. And get that through your thick skull. There's no such other notion of ether than that one. Bunch of particles.
Well, again, there's other notions of how the universe functions with particles than that particle theory. So again, they're maligning particles by saying all particles have to be connected to each other. All particles have to influence each other. And no, they don't. The model can work just fine with a bunch of little bits of momentum moving straight paths through space. That model works.
Okay, so let's see where I'm at here. One fella tried to, or a couple fellas tried to.
All right, it goes on to Michelson-Morley now. All right, so we don't need to hear that, and we got a lot to get through. So we'll move along. But I just wanted to make the distinction because it's very annoying to have people tell you that ether doesn't work or a particle model, ether is particles, when it's a really bad description of particles. Again, straight line is such an important concept, and I'd argue that that's the only thing the universe knows how to do is make straight lines. And it just accidentally, does the spirograph thing. It does the thing where the straight lines end up creating curved lines and other kinds of paths. And that emerges out of the function. But the basic function is just momentum moving straight lines. And that's all you need. As long as you put something in there that causes the force, the straight lines, to be reflected or to be deflected. Once you can deflect the straight lines, then you can create all kinds of complexity. You can create traps. Yeah, where stuff is moving, but it's not going anywhere. Not getting anywhere. And that's all you need to understand how energy is stored in the universe. Alright, so on to Van Briesen. This should be the first video. Yeah. Just horrible again, this Einstein crap. So, let's do some of this nonsense of equivalency principles.
Electron line, it all started here. This is where Einstein began to think that there's something different about the concept of gravity other than what Newton proposed in general theory and general equation of gravity.
Right, so Newton posed no theory. He said, I posit no explanation, because he didn't have any evidence to support one. He could have said angels, he could have said gremlins. He did basically say, I think it's pretty reliable to say it's not spooky action. It's not just magical happening, that something's causing the effect.
So, what's the difference? He called it the equivalent principle. In other words, if we have a situation like this, where two people are on the earth and they're playing a ball game, they're throwing the ball back and forth from experience and have...
Right, from physics, what we can know is they're being affected essentially by two forces. The force of gravity is, pushing, and it is pushing them down because of the lack of force coming from below. There's an uneven amount of force on them from the universe. So there's a tiny little bits of energy raining down on them, and there's more of it raining down from above them than there is from below them, and so they are accelerating. They're moving down. Now, when they move down, there's matter there, and the ping pong paddles below you, have force between them. All the atoms have electrons. The electrons are repelling. They're all doing this thing of capturing energy between them. And as soon as you attempt to compress them, they fight back. It creates more energy in the compressed space. The compressed space fights back. And you reach an equilibrium, state where the gravity keeps pushing you down and the ground keeps pushing you up, and you just essentially bounce or vibrate in that constant tension between the fact that there's more pressure above you and the fact that you keep creating more pressure below you because of the matter below you. And the only force we feel is the force pushing us back up. we don't feel the force pushing us down. So there is no equivalency even in the forces we're being affected by. So even without analogy to a spaceship or anything else, you can kind of understand that the only reason why you feel anything is because of the ground pushing back, but you wouldn't feel the gravity. The gravity goes right through you, moves you on the nuclear level, the subnuclear level, the electrons and protons, and the ground pushes only on your feet. Okay? It pushes on your atoms and causes your atoms to have to rearrange, and that's why you feel it through your whole body, is because it's not a nuclear force, it's a chemical force. It's dealing with atoms, it's pushing on atoms, it's not pushing on electrons and protons. So there is nothing equivalent. We can tell the difference between gravity moving us and the ground moving us. We can tell the difference.
Having lived on an Earth with gravity, they pretty well know what that ball is going to do and how they need to toss the ball back and forth in order to be able to play a game. Einstein claimed, and this was
So he's saying playing a game, he's using that as a metaphor for an experiment where you could detect what the physical forces are that you're being affected by playing the game, by throwing the ball. It's a very crude and simple experiment, and it's not very complicated, and therefore it's not going to tell you much. But the truth is, we can tell the difference. We can be a test instrument. We don't need to play a game. You just need to sit in a chair and say, what force do I feel? The force pushing me down or the force pushing on your ass? Up on your ass.
amazing because at the time that Einstein thought about these theories, it was long before any sort of rockets and spaceships had been sent into space. But he imagined if you could have a vehicle like this that traveled through space and that could turn on engines so that the object, that the vehicle could accelerate at the acceleration due to gravity.
So let's understand, you're just duplicating one of the forces. And which one are you duplicating? Oh, the one pushing you from your feet or your ass, not the gravity. So you're not duplicating gravity in any way. You're not hitting your subatomic particles with a rain of energy, momentum, where you wouldn't feel a thing. No, you're pushing the floor, a floor made of atoms and matter. You're pushing matter into you. You're not having a force push on your matter. You're having material object push on your matter. So obviously very different things, not equivalent at all. This should never have even been something Einstein would speculate about, is that there's any equivalency between the particulate quantum force applying momentum to an object and material objects interacting with each other. The two things can't be equivalent.
0.8 meters per second square, that the very same two people could be inside the spaceship playing the very same game and they would not be able to tell the difference. That's the principle of equivalence. They would not know if there were no windows and there was no realization of being on the spaceship. Whenever they experienced gravitationally any experiment they could possibly do on board of the spaceship versus on the Earth, the result would be exactly the same.
So again, it wouldn't be. If you're accelerating, you're certainly going to feel the floor pushing up on you. You're going to feel your acceleration when matter accelerates you. You won't feel your acceleration if an actual force moves you.
Timing, the falling, everything about what happens here and here would be identical. You could not tell the difference. Now, the real difference is that here you are indeed on the Earth. There's indeed an acceleration due to gravity. There's a force of gravity. But in space, far away from any...
So again, he doesn't say anything about there's also a pressure being created on the surface of the Earth. The atoms are being pushed. And by pushing them, they compress. And when they compress, they create an equal but opposite pressure pushing in the opposite direction. So there's just no concession to the obvious that these two people are being affected by two forces and aren't moving. These two people are moving in space, and they're only being pushed by one force, and that force has to go through their body from the feet or the ass first.
Planets and stars and anything else that could cause the effect of gravity. If the spaceship were to no longer accelerate or simply drift in space, everything would be weightless. People would just be floating around the spaceship, and you couldn't play that very same game. But the moment the spaceship begins to accelerate, at 9.8 meters per second square, the effect would be such that gravity would be felt in the very same way that gravity would be felt on the Earth. Matter of fact,
Right, but it isn't the same at all. Again, so there is no gravity. There's only one force, and you're just duplicating the equal but opposite reaction of the matter. So it's just so wrong to do this. I mean, it's just so inaccurate a way of describing the real circumstance, and to imply that gravity, when there's a counter object in your way and you're not allowed to be accelerated by your gravity freely, clearly the opposing force is the one you're feeling, not the gravity.
you could not tell the difference. And because of that, Einstein began to think that there was something different about the concept of gravity as being forces between two objects. So, carry that a little bit further. Here, let's do another experiment. Let's say we're inside a house, and it turns out that some of our kids used to play that game. We have a place in our house where the hallways.
So they have to make it all very simple and, blah, blah, blah. And it's physics. It shouldn't be made this simple. They're oversimplifying and losing the real important details.
Kind of narrow, but we have two vertical walls side by side, and then we take some of those little super balls, the ones that bounce really well, and then we take it and then we throw it as hard as they could in one direction against the wall, and then the ball would bounce back and forth and eventually hit the ground. The object of the game was to throw it the hardest possible so you have the maximum number of bounces before it hits the ground. Whoever could do that was the winner of the game.
Yeah, tic-tac-toe, really. I mean, it's just ways of cheating.
So you can imagine the game where you throw a super ball back and forth and it would bounce back, but in subsequent travels across the hallway, the ball would fall more and more each time, and eventually the ball would hit the ground, because the ball, of course, is accelerating towards the Earth. Well, we could play that very same game in that spaceship. We could build two vertical walls, we could go in the spaceship far away from the Earth or any other planet or moon, and we could then, of course, since there's no gravity felt there in any other way, we can then accelerate the spaceship at g, 9.8 meters per second square. Again, take that ball, throw it against the one wall, and we could see the ball going back and forth, fall into the Earth as it did in the exact.
Again, seeing it from only the place you're going to see that, okay, is from a place where you're not either connected to the spaceship. If you're inside the spaceship, you're going to move with the walls of the spaceship, and yes, from your perspective, it's going to look like the ball's moving down. But clearly, you can know, if I drew it in real space, that the light goes straight back and forth, and it never changes its path. Okay, the only thing changing is the surface of the spaceship. The light is in the same piece of space. It's a straight line again, a straight line that there's no reason to think the illusion of watching the target and the emitter move away. That doesn't mean that the light is moving in some sort of unstraight manner. And so you would never even be able to do the experiment because light is polarized. You'd widen the polarization, it'd be unviewable. All kinds of things would happen if you attempted to do this even. So, I mean, all of those details are lost. You're moving the emitter as well as the receiver, which means, the continuity of the photon is going to be completely lost.
Same way as in the hallway of our house. Wow. Again, the principle of equivalence. You could not tell the difference.
So, again, the obvious difference is you could sit here and know you were accelerating because your ship will leave the photons. Okay, I mean, that's what it's going to do. The photon's going to go in a straight line. You're going to be able to see it. You're going to be able to see. So whatever amount of arc you see in this path of the light, that arc is going to tell you exactly how fast you're going. It's going to be a speedometer. So, of course, you can tell you're accelerating. In real space, the photon stays in its position, okay, and you'll know that your spaceship is leaving the photon. So, again, this is just a perverse way of looking at it. It's not the right way to look at it.
Now let's take that argument one step more. So Einstein thought about it this way. Let's say we have that same spaceship now, and we have two vertical mirrors instead of walls. And we have a tiny little window at the top of the spaceship and a tiny little hole in the mirror where that window is. And let's say we shine a beam of light into the spaceship. So I need a beam of light going into the spaceship. And it goes through the little hole to the other side, bounces off the mirror, comes back.
So if you're going twice the speed of light, half the speed of light to do this experiment, the problem is the hole moves faster than the light can get through it. So if the light's made of more, if the light has any kind of length, which I think you've got to understand it does, it's going to get broken by the fact the hole's going to move before the whole photon even got through the experiment. So lots of details where you can't do this. It wouldn't even work if we could do it. If we could move something the speed of light, we still couldn't do the experiment because of these limitations. You can't move the emitter to a new location in space. It's like moving. It's like as the energy goes into a radio antenna, if I keep lengthening the antenna, like I'm pulling the atoms away from the electricity that's trying to connect to them, you could understand that the antenna polarization would be monstrous. You would completely change. You would weaken the energy by spreading it over more space. And when you spread the energy over more space, it's obviously it can't do the same thing it would do if it's a laser beam, right? A laser beam versus a light versus, a light scattered over a much larger surface. You can't see the photons when you're taking a small amount of photons and displaying them over a large surface. You don't see any of them.
But since the spaceship is accelerating at g, 9.8 meters per second squared, by the time the light beam makes it back, the hole has gone up a little ways, and instead of going back through the hole and out the window, it hits the mirror on the other side and starts bouncing back, and it bounces back and forth, of course, a whole lot more number of times on the ball, because, of course, the light is traveling much faster, but in essence, the effect would be the same. In subsequent travels across the width of that distance between the two mirrors, you would see the light slowly going down more and more and more.
Right, so you would see. So again, but we already know that what you're seeing is based on you being connected to the spaceship. And if you're not connected to the spaceship, if you're looking at it like this drawing, the thing that should be made out of dotted lines is the spaceship. The spaceship is the thing moving away, and the light just goes back and forth and back and forth. So again, it's just wrong to say it physically happens that way when no, it physically happens completely the opposite. The spaceship moves and the light stays where it is.
Of course, they've exaggerated what it looks like here, but in principle, you'd get the very same result as you have over there. The difference is the ball has mass and the light does not. But because the
so more nonsense about mass, and obviously you can't have momentum without mass, so it's just a silly thing to say. No rest mass. So a photon, when it's not moving, doesn't have any mass. Well, it's never not moving. There's no such thing as a photon not moving. So why play this game that it doesn't have mass? It's just stupid. And then you say it's going to be affected by gravity. Well, how can it be affected by gravity if it doesn't have any mass? I mean, it's just,
principle of equivalence, Einstein said that makes no difference. An object doesn't have to have mass. It can be completely devoid of mass.
Right, just silly. Just absolutely silly to talk about anything being able to impart momentum on an electron certainly has to have mass.
Like light, like a photon of light, and they would simply go across in the exact same fashion as the superballs. So therefore, because of the principle of equivalence, there's no difference in the effect on light as opposed to the effect on object.
Well, right, and the difference is the object is the thing moving through space, and in this case, the object isn't moving. So there are clear differences, and the differences can be detected, and it's just, like I said, I don't even know why Einstein attempted this bold claim, because I don't see what purpose it serves at all. There's just no need for any notion of equivalence between having your subatomic, having my electrons and protons pushed by a force, and having my atoms moved by interaction with more atoms. Clearly, those two things are very different things, and we can detect which one is happening.
And there's no difference in being on the Earth where the acceleration of the gravity is equal to g, or being in a spaceship that creates the essence, the acceleration equal to g. And because of that, he had a very different way of looking at the concept of gravity, and this was, in essence, the birth of the concept of the general theory of relativity.
Says him. I mean, I don't know if Einstein really connected all these dots at all. I mean, again, bent space is a vacuous explanation. It's just instead of saying spooky action, you say bent space. I mean, it's the same thing. It doesn't explain a mechanism at all. We know that it's an energetic event. We know that the Earth moves, that matter moves. Well, why does it move? Well, a force has to act on it. Something has to act on it. To say it just magically does it because the electrons and protons all know they're supposed to move. They somehow they've been given the ticket that says move. What ticket?
You must hand it to him. It was amazing to take that and then carry that thought further. Now, of course, when he proposed that, nobody believed him. Of course, I'm not sure if it's 100% that didn't believe him, but the vast majority of the scientific community...
Right, so this whole bullshit would never have been the bullshit we're talking about now if it wasn't for this crappy Eddington experiment. That's basically what he's conceding. That, yes, science would have taken its time and it would have analyzed this and picked at it a little bit before jumping to it. And the reason why everybody jumped to it is because, oh, the magic has to be true because Einstein predicted that light is twice as bent by gravity. And who would have figured that out? Who the hell would ever say that is true? The only thing affected twice as much by gravity in the universe is the photon, the thing moving the fastest that's supposed to have, that has indeterminate mass. So it has a questionable mass and it's moved twice as much. Now the magneton isn't moved, or the electron or whatever is creating all these other forces. Somehow they're not bent by gravity, just this magic little photon. Only one kind of force moving the speed of light in the universe is affected this special way. Who would have believed that would be a truth? And then we had this very poor experiment hyped as a perfect experiment, and somehow it proved Einstein right, and it didn't do anything close to that. And Einstein was in fact wrong.
He simply did not accept his proposal that light was affected by gravity. They said that's simply impossible. Well,
there's no reason to believe. There's just no good logical theory that explains why this one special manifestation of force, right? And that's what light is. It's a manifestation of force. Just like the virtual photon, that's why they call it a virtual photon. It's because the energy holding atoms together seems so much like this force of light, and that's moving this speed. They all have this consistent speed, and yet they have this incredibly inconsistent reaction to gravity. It just doesn't make any sense. There's no reason to think that would happen.
he was able to prove it in 1919.
No, he didn't prove anything.
So, if you're interested in how we proved it and how we became world famous because of that proof, stay tuned for the next video, and we'll show you what happened in 1919.
So now he has outtakes in here.
No, it was a little bit after World War II. No, World War One. Yeah, but that was not relative to that experiment.
It sort of was, because the first effort was ruined by the war. So Eddington wouldn't even have been meaningful if the first expedition by another guy would have been successful. But the war got in the way. Anyway, so now we'll do the next video. So I haven't watched this yet, but I know I'm going to hate it. Yeah, I'm going to hate it a lot. So this is Eddington's experiment. Now it looks like he's doing the same damn thing the Fermilab guy did. Look at this frickin' drawing. He has him seeing a star behind the sun. That didn't happen. I mean, it's literally this bad that they have to way exaggerate what happened. And now they have the sun. They're saying, oh, I saw something that was behind the sun. Eddington didn't do that. He saw a star that was supposed to be here, and he saw it here. Okay, out here, way past the corona of the sun, way out here somewhere. He saw a tiny little difference in where the star should have been. Tiny little difference. And look at what they draw. I mean, it's pathetically bad physics. I mean, why can't I call this a lie? I mean, isn't this a lie? If you're saying it's this dramatic thing where we're seeing something that's behind the sun, isn't that a dramatic statement? And, worthy of saying, no way. I mean, that's not what the experiment showed.
Welcome to our lecture online. So how do you get the whole world out?
Oh, he's got his drawing on top of him now, which I don't know if that's exactly brilliant.
Doesn't believe you to change their mind. Well, Einstein found the way to do so. He had come with the...
Yeah, he didn't find the way. He didn't suggest the way. Eddington did all of this. Eddington was a believer. Okay, he fell for this stupid, throw a weight on a sheet and it bends the sheet, and yes, that's gravity. Yes, I'm using gravity to model gravity. Yeah, so he fell for it for whatever dumbass reason, and he was hyper to be part of it and to prove it. So he clearly wasn't the most objective person to be doing the experiment, right? He was a believer before anybody else. He was an advocate, a respecter, and then he's the one who's going to be responsible for producing the proof, and that's just not a very good scenario.
Principle of equivalence, saying that curvature of space is what causes gravity, and because of that, light is affected by gravity.
So curvature of space, curvature of nothing. So again, Einstein said, imagining the universe without ether is impossible, right? So, I mean, they're all etherists. They all think this is made out of some kind of jello. And there's no jello.
As well. And so at that point, nobody believed him. Maybe a few people did, but by and large, the general scientific community around the world did.
Because it's a nothing answer. Bent space is saying absolutely nothing about a physical mechanism. So yes, it's just ruining physics because now you've said screw physical. It's magical. It's a magical explanation. It's spooky action all over the place. It's just some spooky notion that the electron needs to go, it has to flow with the vacuum that seems to be in there's a little vacuum cleaner inside of matter, and it's pulling the ether in, and the matter has to go with the flow of the pulling ether. It's mush.
Did not believe Einstein and did not believe that light was actually affected by gravity. But then he told him, I can prove it to you. And he
didn't do any of that. So again, just make up the story. That's not what happened. Okay, he heard about, Eddington suggested this is a way, and Einstein said, super, go for it, thank you. And waited for them to, do it. So that's all. But Einstein didn't have a damn thing to do. He didn't finance it. He didn't help promote it. He didn't do a damn thing.
Did in 1919. So what happened in 1919 was that there was a total solar eclipse that was going to occur off the coast of South America. So they...
Yeah, not exactly, because it's not unlike the one over North America a couple of years ago on the 100th anniversary of this silly experiment, the perfect eclipse over, perfect weather, and a 12 o'clock eclipse, the shortest amount of atmosphere you can get. I mean, so perfect. 12 noon eclipse. Eddington didn't even have that.
They got an expedition together, chartered a boat, and traveled down to the coast of South America. But 6 months before that...
And there were two of them in two different locations, so that's also let's understand the truth.
When the Earth was in this position, he told everybody, take pictures of the sky at night and have the stars, the bright stars in front of you, located on those pictures. So they did, and let's say that the black crosses right here are the representation of the stars they had pictured. Then he said, 6 months later, when the Earth is on the other side of the sun, of course you can't see those stars anymore unless there's a total solar eclipse. And one day, known ahead of time, it's at the coast of South America, the moon blocked the light of the sun. And at that moment, for a few minutes, they were able to see the sky darken again, and the brightest of the stars would reappear.
Right, so this just has to do with getting rid of the scatter that the atmosphere causes. So again, this experiment could be done from space right now with just even just average, technology, satellite camera technology on the average satellite could do the experiment today, okay, and no problems because there's no atmosphere to screw the game.
He told him, take a picture again, and the stars will have changed their position relative to the other stars, not affected by this because they were at different locations in the sky. So what happened was, for example, this star right here, you can see that 6 months earlier, the light went directly to the Earth. Now, the distance from here to here is so small that the angle, of course, would not change whether or not...
Well, I mean, it's not exactly small. So again, the change in position of the Earth is still a relative change, but obviously the distance to the star is incredible. By that standard, these distances become kind of irrelevant. But they still are real distance differences. It's still a different perspective. Not significantly different, but different enough to just say it's different.
that the Earth was here or here, that star will look in exactly the same location, because that small distance, twice the distance between the Earth and the Sun, 2 astronomical units, would not affect these enormous distances to stars, which are hundreds of thousands of times or millions of times the distance between Earth and the Sun. But if the
So it gives you some perspective that you can change your position rather radically and see the object exactly the same. That's how little of the object we're actually seeing, is that it's so distant that, in a sense, the object can be in a whole lot of different locations, and we see it as one location. When we're locating it in a gigantic space that it could occupy. Its exact position is, could be anything within maybe a light year or more.
light had to travel past the Sun to reach the Earth, Einstein predicted that.
Okay, he said past the sun. So again, it's just this, the experiment has to be done outside the sun's corona, or you have no experiment. So the idea is you have to go a full radius outside of the sun. That's where you have to be looking. You have to be looking at a star outside the corona, because the corona is full of particles, scatter, all of that kind of stuff. So you're not going to see anything accurately in the sun's corona. That was already known. So it had to be something viewed out here where the space is more empty. And so nothing behind anything, nothing like that.
The gravitational field around the Sun, the warping of space, would cause the light to change direction. And as
So this makes it understandable. Like, look, the gravity on the surface of the sun, at the surface, is only 80 meters per second. So it's only 8 times the gravity on the Earth. So obviously, with such a big atmosphere, the sun has an atmosphere that's huge. The Earth has a tiny sliver of 1% of the Earth's diameter, less than that, is the thickness of the Earth's atmosphere. The sun has an atmosphere that's a whole radius. So it's a gigantically thick atmosphere, so to speak. Viewing atmosphere, whatever you want to call it, deflecting atmosphere. So you'd almost be better off doing this experiment against something like Jupiter, which has a much smaller atmosphere, viewable atmosphere. And even though you only have 20 meters per second, where the atmosphere gets clear around Jupiter, that's still more than you have a radius away from the surface of the sun, which turns out to be 20 also.
the light then approached the Earth at a different angle,
20 meters per second. So you're way out here getting 20 meter per second. So it's only twice the gravity of the surface of the Earth. It's not much gravity that you're trying to bend it in, where you have to look. And nobody talks about these facts.
any observation, be it with pictures, be it with telescopes, be it with the eye, would imagine.
So let's understand that this experiment has never been successfully duplicated. So one of the fundamental rules of science is that you have to be able to duplicate these results. You have to confirm them, and best if you confirm them with many different modes of experimentation, and none of that's taken place here. Every bit of other data comes from inside the corona of the sun. NASA, when it sees bent light, it sees it inside the sun's corona, never outside the sun's corona. All of these facts just ignored. Obviously, I would say it's not being bent when it's inside the sun's corona. The logical explanation is that you're seeing scatter.
And of course, it's not really imagination. It's because of the changing of the direction of the light, it looked as if the star was now in a different location instead of here. This is now the new visible location of the star.
So obviously, every time somebody makes these arguments, they never show any of the data. So it was 1919. I mean, it was photographic plates. Yet we don't see any of this startling evidence. We don't see any of this proof, because the proof is so marginal, and there's all kinds of questions regarding the integrity of the experiment. Eddington his own journal, he says it, I wouldn't stake my life on these results. He got 10% of the quality of the photographs he was hoping for. 10%. The weather was horrible. I mean, so many reasons to say this is not reason to believe.
Because the light had warped around the sun. It simply had taken a different path because of the curvature of space, the warping of space. And so on the photographs themselves, the star would be at a different location. And sure enough, when they took the picture, they developed it, and they looked at it, they saw that he was correct. The star was now in a different location. Not only that,
it took them months to see it. It was in a different location. So let's understand. It took them months, okay, to manufacture essentially confirmation.
Had predicted the angle at which the star would now appear relative to the previous location, and sure enough, he was correct again. It was an amazing accomplishment.
So again, it was a marginal experiment done marginally. You're marginally capable of detecting this tiny difference. I mean, I could explain it as being able to tell, a nanometer's difference in your pupils at, looking at somebody 20 feet away. It's a tiny, tiny difference, and you have to have a really precise experiment and very perfect results and all this kind of stuff to be able to have any hope of doing it in the first place. And clearly the evidence indicates none of that happened. It wasn't a perfect experiment. It wasn't ideal, wasn't great conditions, wasn't a great eclipse, wasn't a lot of things. And again, let's just understand, in 100 years, they've never duplicated the experiment outside the margin of error. They've never gotten confirmation. They've never tried it from space, which is the obvious more ideal circumstance. You're getting rid of 90% of your error and your noise and your mistakes by getting rid of the atmosphere, and they've never done it from space. Nothing, not one attempt that I know of ever, with all of those satellites, with all of that technology. Never even tried.
An amazing experiment that brought Einstein into world fame, because it was absolutely amazing that he made that prediction from the concept of the equivalence principle. And then how would he take that and take that to a leap of faith?
So the silly notion was, because light looks like it falls down the rocket ship, okay, because it looks like it falls down the rocket ship, Einstein theorized it has to make light fall on Earth. He has to make light fall like it's falling into Earth, so it looks the same as the rocket ship. When the two experiments aren't the same. One's two forces interacting, one's only one force interacting. I mean, it's just too not very smart or logical.
To speak, and predict that light would be affected, the path of light would be affected by gravity in such a way that light itself is affected by gravity.
So the only force affected by gravity, and it's affected twice as much as any material object. And that all makes sense to you, and you all believe it because they say so. And I say it's the silly thing to believe in the first place. The evidence absolutely sucks. No reason to buy into this nonsense at all.
After this experiment, very few people doubted that he was correct. It was an absolute amazing feat. It was an absolute amazing...
So way overstated, right? I mean, it was absolutely amazing that such a garbage experiment could be sold as pristine and great evidence, and we're all believers now. This is worse than a fuzzy cigar image, and you're saying you've proven UFOs and aliens and extraterrestrial intelligence. It's that bad. This is like claiming crop circles proves aliens. I mean, it's that bad.
Discovery, and he gave it an entirely different way of looking at the concept of gravity, and hence the general theory of relativity. Now we're going to see
the mushy theory of magic space, and that's all. It just should be called the mushy theory of magic space. There's no physics here.
Of all the other effects caused by this theory. For example, the motion of Mercury is affected by that general theory of relativity.
No, it's affected by the precession of the sun's center of mass. The sun actually does move. We can't see it because the only part that's moving is internal mass. The distribution of its atoms changes a little bit. And as it changes, it affects Mercury because Mercury is closer. So Mercury precesses much more than the other planets because Mercury is much closer. And it just has to do with, if you understand that the sun's mass is moving, its center of mass, then you understand why Mercury's mass is moving.
And time is affected by general theory of relativity.
So again, more babble about something called the time, and somehow you can affect a time somewhere when time is how fast a force moves distance. And it never changes, and the force always moves the same distance in the same amount of time, and that's never, they have no evidence of a force ever doing anything otherwise. So this is all just bullshit.
So you'll see that there's all kinds of effects that we can actually measure and see, again, proving over and over and over again.
No, that never happens. Proving over and over and over again thing never happened. You just keep using, connecting unrelated dots and pretending they confirm each other. So it's like doing the two-slit experiment with radar, and it's the explanation can be as simple as jamming, and it explains it perfectly. Yet you pretend it's the same experiment, and then you pretend you did the same thing, and it created the same pattern, and it didn't do any of those things.
This theory is absolutely correct.
See, it's absolutely correct because we have this terribly marginal evidence and this terribly extraordinary claim of magic. So physics is magic, magic forces, magic movement, magic, magic, magic. It's just a religion. It's horrible. It's disgusting. The more I think about it, the more depressing it is that smart people fall for this crap.
That space is indeed curved or warped, causing the
curved or warped or bent or crookedy. Yeah, in 3 dimensions it's basically vacuum cleaner. Okay, so yeah, in 3 dimensions it's just a convergence. It's the opposite of a light bulb. That's all it is. The magical opposite of a light bulb force. It hits you and makes you move towards it. The magic baseball. You throw it at something, and when you hit the object moves towards you. Ooh, magic.
Effect of gravity. It's an amazing discovery.
It's amazing that you fell for it.
And this is how we proved it.
And you really didn't prove a goddamn thing, and you know it. You really have to know how bad this evidence is. They've got to know how bad it is. And the fact that he can't even describe this accurately, that the tiny amount of gravity that's deflecting the light, 20 meters per second per second. The gravity where Eddington was looking, the gravity that was bending the light, is only 20 meters per second gravity. It's only twice the gravity on Earth. That's why Einstein doubled it. It's a terribly small change.
Pretty amazing.
Pretty stupid. I don't know why he leaves these outtakes in here, or these after jokes.
If I remember right, he was pretty bored with class. He didn't want to go to class. They just bored him to death with equations and theories, and he didn't care about that. He wanted to uncover the universe.
Yes, concepts are so much more interesting than stupid formalizations. Knowing how to calculate the exact mass of this little clump of hair, who cares? Okay, but understanding what it was made out of, and the static electric charges and all the other interesting stuff, well, that's so much better.
Which he did. So don't bore smart kids like that. Give them some expense to discover these things.
Yeah, whatever. Give them some excuse to waste time. Einstein wasted a lot of time. you could see that, frankly, before and after. Alright, so that was pretty horrible. Alright, so, this is so depressing that, again, it's just such hype. It's all just hype. They have evidence from hype. Again, this is just, these are advocates. It's like the UFO nuts. You know, it's like the truthers, the 9/11 truthers. You know, they got their little photograph of, oh look, it's bombs on the plane. You know, all kinds of, anything that just looks like it a little tiny bit, and they just latch onto it because they want to believe for some dopey, dumbass reason for which I cannot understand. It's a religion that goes absolutely nowhere. Randomness is controlling our universe. How exciting! The randomness! Yay! It's like celebrating chaos. It's like, what the hell is chaos? Random? What do I need those things for? How are those are good things? You know? I mean, too stupid. So depressing. So anyway, till the next time and such. Oh yes, I did make a video. So yeah, I'll save this for last because then we'll know how many people are really paying attention, give a shit. So I did make a video, which I'll leave a link below. It ended up being 22 minutes, but it's the core of it is some little 8-minute chunk in the middle that will sort of be my argument in the debate, you know, in a week. A little more than that, I guess. And it also just has some of the talking points in it, and so I have to tighten it all up a little bit and all that kind of stuff, but it's just basically the two-slit argument, and you really can't, it's hard to do the two-slit argument without arguing what photons are actually, what they are. You know, but anyway, I certainly can argue that the evidence is hype, that the story is never told without a bunch of hype included. Exaggerations about detector experiments, you know, assumptions about experiments that never really have been performed. I mean, we just have stories of the, you know, experiment. We don't have any evidence of the experiment, that kind of thing. So, the link below to an unlisted video that's just practice, essentially, for the debate and such. Oh, till the next time and such.